So today we'll be going over another Diophantine equation technique called the squeeze method. And actually, the video will be really short today because we're going to be looking at a specific technique in the squeeze method. Like this is not the only technique. There are other stuff, and hopefully I will make another video where we have more advanced problems. But since I want to kind of emphasize the bounding, this kind of like kind of emphasize the technique through basic problems to show the importance of it more. I'll just do really simple problems, and hopefully we'll get to do more complex problems that are much spicier than the ones we do today. So the squeeze method is all about bounding, and actually it's not. So normally it's about what do you say, like you can show that there's no solutions. You can show that there's so I'll have to show through examples to make it much clearer to you guys. So the first example is y squared equals x squared plus x plus 1, where x and y are integers. So those of you who watched my previous videos, you'll realize that this is in the form of x squared plus ax plus y squared plus bx equals a constant. But the problem is that, remember this is supposed to be 2a and 2b. And a and b have to be positive integers. So a and b have to be integers. So in this case, a would be equal to half because 2a is equal to 1. So this sort of like factorization to make it into sum of squares, or in this case difference of squares, is not possible. So therefore we cannot use this, and we're going to use another technique called the squeeze method. So firstly, we're going to go through this a bit slowly, though it's a really simple problem, to kind of understand how we think of this method. So firstly, y squared. So we're going to take a different approach this time. We're not going to try to make difference of squares or sum of squares because we don't think it really works. We're going to see if there's another method because we think that will be the other intention of this problem. So firstly, so we know that y is an integer, so y squared is equal to this. So we want to express this. We want to express x squared plus x plus 1 as an integer expression squared. Then y will be equal to that integer inside. So what happens is we want to try to express x squared plus x plus 1 as an integer squared. But we can't, because x squared plus x plus 1 isn't a square of some expression in x. However, we see that x squared is a square of an integer, and x squared, and we realize that this actually looks kind of similar to quite similar to x squared plus 2x plus 1. So if we just add x, then x squared plus 2x plus 1, it becomes x squared plus 2x plus 1, which we know that is equal to x plus 1 squared. And you'll be like, why are we looking at this? Because we then know that x squared plus 2x plus 1 is a square of an integer as well. So, and x is a positive integer. Okay, x is a positive integer. Sorry, I should have emphasized that. X and y are positive integers, which means that x squared plus 2x plus 1 must be bigger than x squared plus x plus 1, because if we add x to get this, then this must be bigger. And of course x squared is smaller than x squared plus x plus 1. So if we minus x, so we found the square of an integer expression in x that is smaller than this, and a square of an integer expression in x that is bigger than our given expression. So we get that x squared plus x plus 1 is between these two. It's smaller than this and bigger than this. So we found two square expressions in terms of x that kind of bound x and bound this expression. But then now is the crucial part. So x squared So we're going to rewrite this. And we're going to rewrite this as x plus 1 squared. And try to think about this carefully. So x squared and x plus 1 squared are consecutive squares. And because, for example, like 2 squared and 3 squared are consecutive squares because 3 is one more than 2. Therefore, 3 squared is the next square after 2 squared, which means that if they're consecutive squares, then, okay, I'm not going to erase that because I need to explain this. That means that there can be no square expression. There can be no positive square integer between two consecutive squares. But x squared and x plus 1 squared are 2 consecutive squares, but then x squared plus x plus 1 is a square integer. But it cannot be because it is between 2 consecutive squares, which means that this can never be a square expression of an integer. So we arrive at the solution that there is no solution. So that kind of happens, since that might have happened really fast for some people, because, this technique of bounding is kind of pretty unusual, I guess. So like this, we can kind of see really the importance of this. So we took advantage of the fact that x and y are positive integers, and we know that this must be a square of an integer. This must be a square of an integer. So we want to try to find obvious square positive integers in terms of x. So x squared is obviously a square number. X squared plus 2x plus 1 is obviously a square number. We found 2 obvious squares that bound x squared plus x plus 1, and then we use that to cancel all cases, and it turns out these are consecutive squares, so there is no solution. So you actually see these kind of problems quite often where you bound it, you do the squeeze method, you squeeze it into a boundary, and then you show that there's no such solution. And this is a really common technique. But, well, maybe I'll make another video on this. But let's say this is another problem. An example problem. Don't confuse yourself with this problem. So what do we get, like, okay, I'll just say, okay, so let's say like some polynomial in x is bounded between x squared and x squared plus 4x plus 4. It's bounded between these two. Then, and we know that y squared equals p of x. So p of x must be a square of an integer, but it's between these two. But this time, these are not consecutive squares, because this is x plus 2 squared. But it's between these two, which means that the only square between these two squares is x plus 1 squared. Which is pretty obvious, because, like, if you order out all the squares, the only square between x squared and x plus 2 squared will be x plus 1 squared. So p of x is x plus 1 squared. P of x is x plus 1 squared. And then you'll be able to solve x, and then maybe you'll hopefully find y. So like this, you can find, so in this case, we didn't get a no solution. We got at this part by squeezing it and then reducing the number of cases, like reducing maybe you will not get just one, but 2 possible expressions and possible equations. So it depends really. So in this case, we only got 1, but in this case, we got 0. So the squeeze method is not only about showing that there's no solution, but also that there might be only one solution. So yeah, actually I'll just leave that there so that you can kind of pause and ponder for a bit. So yeah, so I think we won't need to do an example problem because it's quite similar to this. I think the main takeaway, I just want to make it a bit more flexible. So it's all about bounding and trying to reduce the number of cases, because integers, well, in this case, because positive integers are really specific things, and then positive integer squares are very specific things as well. So you can always restrict the number of cases to make solving the problem much easier. So yeah, that is it for today, and I hope you enjoyed this video, and I hope to see you in my other videos.